So what I'm going to talk to you about is the Ninja Turtle Pizzeria today. So what is this? It's a pizzeria that the Ninja Turtles opened, and they have a very, very simple business model. So what they have is a set of tables. It's a small restaurant. They have only 4 tables named after the Ninja Turtles turtles, exactly. And each table has a number of seats. Then what else? They have very important clients. If you check the names here, they have Madonna, David Beckham, Will Smith, Josh Depp, all people really important. Then, of course, they make pizzas, and they have the list of pizzas there, including the Master Splinter, which is the most sold pizza in the restaurant. Then what they do, every time a client comes in, they sit the client to a specific table, and they record the in time and the out time. And then once the client is sitting at a table, they can start making orders. So they record the order time, and then within an array, the list of pizza IDs that are the foreign key to the pizza table. This is the restaurant business model. How do they implement? Well, I don't know if you know, but Ninja Turtles are a big fan of open source. So what they do is they use a Postgres database to store the information. But then what they do is they also need to propagate this information, because they have other people in the restaurant, let's say the pizza makers and the billing person, that needs to receive the information about an order being generated. So what they do is they have an ETL job running every hour that takes the information from the operational database and pushes to the database where the pizza maker and the billing person are reading. They could use a variety of tools. For the sake of the argument, they took Informatica. It's an ETL tool that allows you to create data pipelines between systems. What's the output of that data pipeline? The output is an order summary, where we have the client and table information together with, within that order, the list of pizza names and amount that someone has to pay. So the pizza makers know which pizza to make, and the billing person knows how much to charge. If you do that in Informatica, it has a nice UI, maybe back in the 80s, that allows you to drag and drop filters, joins, connectors, all in visual mode. But this is not the most important part of using a tool like Informatica. The most important part of using a tool like Informatica is that a lot of these ETL tools, they understand and they know really well the source system and the capabilities of the source system. So what those ETL tools allow you to do is they allow you to just with a GUI write the flow, and they will use all the features of the source system to extract the data in the best way. So if you write something like this in Informatica, the end result will be a code that looks like this. There will be a select statement on top of Postgres from the orders table, join the table assignment table, join the pizza, join the clients, join the tables table, and it will use all the features of Postgres that are available in Postgres itself, including the join between the pizzas and the order with the any function that allows you basically to explode the array that we had in the orders table in order to join with the foreign key, with the primary key of the pizza table. Now that we resolve all the joins, it's time to select, for example, the order ID, the client name, the table's name, and then just for the sake of the example, we are using some JSON functions in order to build an object that contains the pizza name and the pizza price, and then aggregating that at order level. The group by allows us to aggregate, and last thing that the SQL will do is basically filter for the data appearing in the previous hour. Since we run this ETL every hour, we are willing only to move the data appearing in the source system the previous hour. So we apply a filter like that. The outcome is what we expect. It's exactly what we said before with the order ID, client name, table name, and the list of pizzas. Okay, let's now review how this process works. Between 8 and 9 p.m. is the restaurant busiest hour. So let's say that the batch that was running around 8 o'clock already finished. We are now between 8 and 9, and we start collecting orders. The 9 p.m. arrives, and usually in the batch world, you don't start a batch ETL immediately after the hour. you may wait a couple of minutes to be sure that the source system collected all the data for the previous hour. So let's say that the Ninja Turtles started their ETL at 9:05. And they put a lot of effort designing the ETL, so the ETL runs in just 1 minute, finishing at 9:06. Anybody can see a problem with this approach. The problem is that if we are lucky and we have a customer that made an order at 8:59:59, they will have to wait at least 6 minutes just before the information about the order reaches the pizza makers, reaches the consumers of the information. But in the worst case scenario, that a client makes an order at 8:00:01, they will have to wait for 66 minutes before the pizza makers even know about the order. You can imagine yourself, if you go to a restaurant, you make an order, and for 66 minutes you are sitting there, watching on the other side the chef looking at you and doing nothing. What would you do? Probably walk away after like 5 minutes. So this is the problem for the restaurant. They need to cut down this delay. But it's not only about reducing the batch time, maybe running the batch every 5 minutes instead of every hour. The problem is that what they would like is they would like to inform immediately, as soon as one order is generated, the pizza makers and the billing person. Maybe the billing person is not critical to be informed immediately, but the pizza maker, yes, because you want immediately to start working on the order that you receive. So this is why they want, and a lot of us want, to go streaming. We want to react to every single thing happening in our source systems. And what we will use as tools is Flink. I described it before during the videos. It's a really powerful tool to create data pipelines. Allows you to connect to a variety of source systems, a variety of target systems, and create transformation data pipelines. I would say that Flink is incredible, and you create a lot with it. But the best combination is by associating Flink with Kafka. Why is that? Because Flink is good, can allow you to create data pipelines, but it's kind of a set of information in the data pipeline and the output. If you want to make that output independent and available to a lot of consumers, you can push the output to Apache Kafka, and then you detach basically the transformation from the list of consumers that will be interested from that information. So you achieve a pub sub-architecture where you publish the information, you transform the information, and then if you have 1 or 10 consumers, the information is still there, is still available in Kafka. So what we will do now is we will see how the example that I've been explaining to you can transition from batch into the streaming world. Even more, what I will show you is that you can do that by almost keeping the SQL. The SQL that we saw before that was generated by Informatica will be not exactly the same, but similar to the one that we will use in Flink. Why is this important? It's important because SQL is the language that is spoken by your data analyst, your data engineer, and a lot of other figures within your company. If you can keep the same language and redefine how your data pipelines work, you can achieve a faster time to result, a faster time to validation. So opting for the SQL way could cut a lot of corners in your migration from batch to streaming. Everybody still awake? Okay, so let's start. And what I will show you is a set of scenarios that we will try to implement. The first scenario is basically copying whatever Informatica was doing before, because Informatica was working, why shouldn't we work the same? How can we do that? Well, there is a way in Apache Flink to define JDBC connectors. JDBC is a standard technology to query a source system. So what we could think about doing is we have 5 tables in Postgres. We generate in Flink 5 tables with the JDBC connector pointing to the 5 table in Postgres, and then we write some sort of joining query and we emit the results. okay, let's try to do that. How do I create a table in Flink with the JDBC connector? Well, it's not too complex, because all we have to say is create a table with the columns ID, name, and seats. The connector is the JDBC connector, and then we pass the URL of the Postgres database and the table name. We take this SQL, we do the same SQL or similar SQL for the 5 tables that we had in Postgres, and then we need to write the joining query. And the joining query is extremely simple. Not really, but if you compare this to the query that we had before, generated by Informatica, the changes are minimal. Because the changes in this case are the JSON functions that we are using to create the JSON object and to aggregate it. How do we join the array of pizza IDs that we had in the order together with the IDs of the pizzas? And then how we filter for the previous hour. So 3 changes out of a SQL that was probably 20, 25 lines, not too much. So does this mean that we made it? That we already achieved streaming? That we are ready to party? Well, no, not really. I'm sorry to say that. Because yes, we are using Apache Flink, and yes, the SQL is almost the same that we had before. But the bad news is that if you're using a solution which is purely JDBC based, you are still in the batch world. You're not doing streaming. You are still pulling data every now and then. Even more, we went out of Informatica, we approached Flink, but if you are in the batch world, Informatica had tools like an internal scheduler that you could use in order to decide how often to run a certain job. And I don't think we have that with Flink. So it's batch to batch, it's one-to-one. Well, I believe we are in an even worse situation. Because the problem is that for every table in Flink that we are defining pointing to a table in Postgres, we need to define which is the database URL, which is the username, which is the password. For Flink, those 5 connections could be from 5 different databases. So what Flink will issue is isolated queries. They will not be part of the same transaction. There will be potentially no consistency. Even more, what we will see is that Flink, because not knowing that they are part of the same database, what Flink needs to do is retrieve all the data from all the tables and try to solve the join locally. Cannot apply predicate pushdown. So we are going to receive a lot of unfiltered data. As I said, this is due to the fact that those 5 connections are independent. There is no way in Flink to say all those 5 are coming from the same data source. So what we see on the database is a lot of unfiltered data, a lot of unfiltered queries that are retrieving a lot of data, and with possibly the problem of running out of space. Okay, so we changed the tool, we developed a new solution, and now nothing is working. We lost everything. We are still doing batch, and even worse, we are doing batch with wrong data because there is no consistency. So let's try to improve the situation, starting to try to improve the consistency of our results. How do we do that? Well, what if we source the data from the database, which is already consistent? So what we could do is, instead of writing 5 JDBC connectors, we write just 1, and we use the SQL that was generated by Informatica to create a view. So we are reading from the view, which is consistent, and we are pushing to Flink and selecting the fields and pushing the results. The good thing is, as I said, the SQL of the view here is exactly the SQL that was generated by Informatica, so we can more or less take that for granted. On the other side, the SQL that we have in Flink is extremely easy, I would say, because we need only to select the fields and filter for the previous hour. Basically, what we were doing with the Informatica SQL. So how are we now? We have an easy SQL query using Flink. We have consistent data because now we are reading from 1 unique view instead of 5 different tables. But unfortunately, we are still doing batching. So this means that we potentially require an external scheduler, and potentially we are moving a lot of data. because every batch time, we retrieve all the orders of the previous hour. We are not doing streaming. So let's try to do it. How can we do this? Okay, let's keep the design that we had so far. But now, what we need to think is, which is the table that changes more often? And the table that changes more often is the order table, right? So what we could do is try to get a feed of all the changes happening to the order table as soon as they happen, and then try to, on a second time, try to get the entirety of the entire order. How can we implement this? Well, what we can do is, instead of creating a JDBC connection, we create a CDC connector, a change data capture connection to the order table. This is done with the CDC connector, sorry. What we are doing is, instead of querying the table, we are reading the database log. As soon as a change happens in the order table, we move that information into Flink. But then what we have in the order CDC in Flink is just a row representation of the order. We need the full picture of the order, including all the joins with all the other tables. So what we can do is, as soon as we receive the row feed, we can do a lookup to the joining view, retrieve the full order status, then join this data and emit the result. How do we do this? Well, first of all, we need to define a CDC connector. But again, the SQL is not way off what we had with the JDBC connector. The SQL here, it just says it's now Postgres CDC instead of JDBC, and the list of parameters is almost one-to-one. But then, how do we perform this lookup every time that we receive the row feed of the orders? Again, the SQL is not complex. It's almost the same that we had before. The only change is in the join. And if you check the join here, it says select the columns from order CDC, join order and reach in for system time as of order and reach in proc time. So it's using the processing time, it's using the time now to say every time I receive a new order, I will do the lookup now. And this is basically a lookup join. The good news here is that if, for example, we receive from the CDC channel the information that a new order with ID 12345 has been generated, when we execute the lookup, the filter will be applied to the query. So we will retrieve just one row at a time from the view. We are not going to scan the entire view and retrieve the entire view. So we are applying what Informatica was doing in predicate pushdown. So, I mean, this looks interesting. We are doing streaming. Are we okay? Are we ready for partying now? Because yes, we are doing streaming, and we are reading consistent data from the database. Yeah, we are maybe reading 2 times from the database, one from the log and one via JDBC connector, but that's not too much of an issue. But the problem here is, are we really sure that we are producing consistent data? Check this out. So this is the flow in theory. We have an order with ID 100 and pizzas 233, whatever the pizza names are. As soon as the order is generated, we get the feed of this order being generated via the order CDC connector. And then we fire up the JDBC view, the JDBC lookup. We join the result and we emit. We join the data and we emit the results. This is in theory. Now, check this little detail. We have order 100 arriving. The CDC connector senses it. But just before we fire the JDBC lookup, we have an update on our order. Now the pizza is no longer 233, pizza is 111. What the JDBC will do is we'll look up in the database and check that it's 111. The joining query will propagate the data, and the result will be that order 100 is 111. Even more, since we had an update, the CDC will sense the update. We will fire the lookup again, and we will join the data, emit the result, and we will showcase another time order 100, 111. So we are pushing to the consumer 2 times the updated version of the data in the database. Is this a problem? The answer is it depends. In the Turtle Ninja use case, at the end of the day, the pizza makers need to do just the 111 situation. They don't really care about the 233 situation. But in your business, it depends on, can you push 2 times the updated result? Or do you need to always push whatever was in the database at the specific time? If it's the second case, well, you have a problem here. How can we solve this? And I believe the next slide will make someone happy. We can solve this if, for example, we are able to query the database and ask the database what was the situation of this order at this particular time or transaction ID. This is what is called in Oracle flashback query. And this statement has been asked on Twitter by someone that you saw on the stage with me before. It's my friend Gunnar. And what he is asking there is saying, is there this kind of flashback query capability available in a lot of databases? If you check the replies, the result is, again, it depends. Because some databases will allow you to perform this kind of flashback queries based on the transaction IDs. Some other databases will allow you to do the same based on transaction time. Postgres, by default, doesn't have this capability. You can build it around if you change the design of your table structure, but sometimes you can do that. Sometimes the table structure in Postgres is locked down, so you cannot do that. So we are back point 0. How can we achieve streaming and consistency? Well, if you read online, one of the biggest solutions is to use what is called the outbox pattern. In the outbox pattern, what you do is you pre-package the information before shipping it. It's more or less what we were doing with the view in our Postgres database. The problem with using just a view is that a view doesn't write logs. A view is shown every time you query the database. But what we need is something that is writing a log every time a new order appears. So with the outbox pattern, what we can do is replace the view with a physical table, called in this case, outbox table. And then once we have this outbox table containing the data in the shape that we want already to propagate, we can create a CDC connector. So we have a streaming information coming from the outbox table into our Flink table, and then select the fields that we need and propagate the results. How do we implement this part? Well, first of all, we need to create a table called orders outbox, or whatever you want to call it. This is the outbox table containing exactly the fields that we want to propagate to the target system. But then the problem of the outbox pattern is that now we require to change all the DML operations, all the data manipulation operation. Every time we do an insert, an update, a delete in any of the tables involved in the join, we need also to do the same change in the outbox table. So this means that our insert that before was just an insert statement into the order table now becomes something like this, where at the beginning we do the insert into orders, but then we have also to feed the outbox table. And what this SQL is doing is joining the order table with all the other table in the database to extract the view data and then insert into the outbox table. So with the outbox pattern, what we are achieving is streaming. And we are doing with consistent data because it's coming from the outbox table. So we can include the insert into the outbox table and the insert into the original table within the same transaction. It will always be consistent. We are using the ACID properties of the database. Even more, with the outbox pattern, we also allow to decouple the internal representation of the data, so our 5 tables, to the external representation of the data, which is the outbox table. So we don't leak internal details that we don't want or cannot leak. For example, if we have PII information in the database that we cannot push to a target system, With the outbox table, we can do that. So if you check this, I believe you can start hearing the music of the party, right? But the outbox table is not perfect, in my opinion, because we need to change all the DMLs. All the insert, updates, deletes need to be changed in order to update both the outbox table and the original table. Even more, with the outbox table, we are storing the data twice in the database, which could be a heavy requirement for some of the database and some of the application. Can we at least don't do the second? Can we avoid storing the data twice? Well, if you are with Postgres, you can use a feature called Postgres logical decoding that allows you to write, instead of to a table, allows you to write to the database log. So what you can do then is you write to the database log, and then you use Kafka, the Debezium connector, and Flink to read these messages from the log and emit the results. How do you write to the log? There is a function in Postgres called pg logical emit messages, which accepts 3 parameters. The last one is the JSON order. For what it matters to this function is a string. It's our JSON representation of the order. The second parameter is called myPrefix. It's a prefix that you can use to distinguish this kind of messages from other type of messages. But the most important parameter in here is the first parameter, which is set to true now. What this parameter says, it says that this writing to the log is part of a transaction. So again, what we can do is, like we were doing before, inserting into the order table and inserting into the outbox table. Now we can insert into the order table and we can write to the log. Within a transaction, we achieve always consistency. How do we make sense of this data in Flink? Well, we need to perform a couple of things. First of all, we need to decode the data, because the data that we write to the log is automatically encoded, and we can use the function from base 64. And then, since we package the information as a JSON object, we need to retrieve all the fields. But I would say that this kind of SQL is not too hard to write or to keep. So the lights are going. We are ready almost to party because we removed the need of storing the data twice. Yeah, we have still that DML change needed. Can we also remove that need? Well, if we want to remove that need, this means that we have to avoid recreating the consistency in the database, but do that on the Flink side. So what we could use is a feature in Flink called temporal joins, which is basically very similar to what we were doing in the database world with the flashback queries. Let's review how this works. Let's say that we have a pizza, the most sold pizza, Splinter, at $10. Then we do a flash sale, and we put the Splinter pizza at $6. Then, because it's too much of a good offer for our clients, they put the Splinter pizza back at $10. Let's say that Madonna was so lucky that she made in the order when the pizza was at $6. But because the time for the sale was really short, by the time that this message arrives in Flink, the sale is over. So if we perform kind of the lookup now, we will overcharge Madonna for $4. What the temporal join allow us to do, is to say, I want to know the pizza situation, the price situation, where Madonna made the order. So it's using the event time, which is when Madonna made the order, and not the processing time, which is when the order arrives in Flink. So this is a cool feature of Flink that allows you to consistently use the event time to perform all the joins. So how can we implement this? Well, the design looks similar to the original situation, but now we are having CDC flows instead of JDBC flows. So we are doing streaming. And the query, it's not easy, but again, it's not far from what was generated by Informatica, because the top part is exactly the same. This select statement is exactly the same. Bottom part is exactly the same. What changes slightly is here in the middle. but changes only a little bit because there is only a suffix for every join that says for system time as of orders event time. So I'm saying every time I do a join, I want to know the status of the join at the time of the event, doing temporal joins. So if we use this information, well, this method, we also remove the need of doing DML changes. Seems like it's perfect. Seems like we can start inviting our friends to the party, right? I have a bad news. We need to talk. And we need to talk about a feature which is called the watermarks. The watermarks are the way that in Flink, you say that the time is passing. So for example, if you receive an event that has time equal to 4, you can have a watermark that says, I receive all the events until time equal to 4. So when a new event with time equal to 5 arrives, you update the watermark and you update the watermark again. Why this is useful? Because in theory, everything happens in order. But in reality, you could have events happening out of order. So you can also tune in Flink the watermarks to say, well, I received the watermark with t equals to 6, but I know that some events might be late. So I would like to wait a few minutes more in order to wait for events which can arrive late. So why this is relevant? Why am I talking about this? Well, let's say that yesterday night we received the latest order, the Ninja Turtles received the latest order, and then they updated the list of clients in the database, correcting a few typos. They changed the seats at the various tables. They kicked out the latest client, so they noted the timeout. And finally, they change in the list of pizzas and they push up all the prices by €1 because they want to gain more. So the new day arrives and a new order arrives, is generated. What we would expect is that now Flink does all this kind of temporal joins, check with all the other tables that they have the latest status and immediately emits the results because we are doing streaming after all, right? Unfortunately, this doesn't happen. This doesn't happen because we have an updated watermark for the order table, but not for all the other tables. The other tables have still watermarks in the past. So we will not see a new order arriving until we have new watermarks for all the other table, and then we will see a new order showing up. If you think how often you change the menu in a pizzeria, you quickly understand that this is not feasible. We need to find a way to advance the watermark. How do we do that? Well, we have a few options here. The first one is to use a parameter called idle timeout. What this parameter does is, if you don't hear any change for this particular table for a few seconds, advance the watermark. It's a possibility. I would say it's quite risky because we could, for a little bit of lag in the network, advance the watermark a little bit too early. What is the other option? The other option is to advance the watermark by creating some sort of fake load in the original database. So what we could use is database triggers or a tool within Debezium that is called, a feature within Debezium that is called the heartbeat action querying interval. Basically saying every now and then, change a fake row in the pizza table, change a fake row in the clients table, in all the tables, so I get updated watermarks. Okay, this seems interesting because we do streaming, consistent data with temporal join, we solve all the problems. The only problem with this solution is that we are generating additional load in the database, additional fake load in the database just to advance the watermarks. In some cases, this is perfectly fine, but if Flink is not the only reader of information from the database, we need to talk with all the other people accessing the database to tell, look, that the row with table Francesco, it's a fake one. Again, this is a possibility in some use cases. It's not possible in other use cases. Even worse, I would say, are we really sure that we are still doing streaming? If we advance the watermarks every 5 seconds with a trigger, are we still doing batch every 5 seconds? I mean, if we receive every 5 seconds the list of orders, to me, this doesn't like any more streaming. How can we solve this? Well, last attempt. Instead of doing temporal joins, let's use the transaction informations that we have with the CDC connector to try to get a consistent view of the data from the database. Because if we are using, for example, Debezium, what we receive is not the updated version of a single row. We also get the ID of the transaction and the amount of changes happening in a transaction. So what we could do is we could use the transaction ID and the transaction interval, the transaction time to create interval joins between the various tables. And then even better, since we know the amount of changes happening in a single transaction, we can wait until we sensed all the changes happening in a transaction, and then emit the result. If we do this, we are doing streaming with consistent data, no DML change, no additional load in the database. You know, you can start hearing the music of the party. The only problem with this approach is that, for me, it's quite risky, because the query that you will have to write will be a little bit more complex, quite a lot more complex. Because by default, you would expect, you know, transactional are always increasing, time is always increasing. Apart that, that's not. Because transaction IDs with databases like Postgres can restart from 0. What happens if that happens is stuff that you will have to understand all the corner cases, and find a way around it. So there is potentially a lot of complexity in writing the query, and a lot of complexity also in managing the state that could be bigger. So we are almost out of time. I presented you a lot of things, but none of the solutions seems to tick all the boxes. But I believe it's time now for a summary. Because what I've been showing you is 6 opportunities to move from batch to streaming. From direct JDBC, JDBC with views, CDC with JDBC lookup, outbox pattern, temporal, and transactional joins. If we review the solutions, if we are talking about streaming, anything that is purely JDBC based is not streaming. We are still in the batch world. Flink temporal join seems to be streaming, but if we are advancing the watermarks every now and then, to me, is not streaming. For consistency, the direct JDBC connector, just forget it, is not consistent. It issues 5 different queries to the database. The CDC with JDBC lookup seems to be consistent, but if you have fast changes, you are propagating 2 times the new version of the row in the database. DML changes, it's everything good about from the outbox pattern. If you cannot touch the database, you cannot implement the outbox pattern. Additional database load. CDC with JDBC lookup, we are querying the database 2 times. The outbox pattern, we are writing data 2 times, we are storing data 2 times. Flink temporal join, if we want to advance the watermark, we need to create fake load in the database. Finally, is the join simple? Most of the cases, yes, the transactional joins is the tricky one. But at the end of the day, you have a lot of solutions which are SQL. As based on SQL, so you can quickly mock something up, check it, talk with your business analyst, with your data engineer, and quickly evolve. Even more, depending on your constraints, your requirements, your skills, the complexity of the job, and where you want to put the cost. Do you want to put the cost in the database? Do you want to put the cost of recreating the consistency in Flink? You can pick one of the solutions that I highlighted. And I hope that at the end of the day, you will be able to send back to your boss the message, boss, it's done. We move from batch to streaming, and please invite me to the party. I want to leave you with a link to the slides. You will find the slides and also another link to a GitHub repository which contains all the details of the 6 pipelines and the implementation on how you can create those 6 pipelines using Kafka, Postgres, and Flink. And finally, if you want to try them out, please do so at Ivan. We offer Flink, Kafka, and Postgres as managed services on top of all the clouds. Usually you get a $300 trial. Because now I feel that we are friends, you get an extra $100 if you use this QR code or the URL below. At the end of the day, I hope that I convince you that doing from batch to streaming in SQL is doable. I'm Francesco Tisiot, and I'm here for all your questions. Thank you very much.